Okay, for any ray diagram, we start out with a mirror drawn. We have the principal axis. The focal point is located the focal length away from the mirror. This is where all of the parallel light rays will come to a focus. The center of curvature is placed at the center of that sphere. Remember that the center of curvature to the mirror is the radius of the sphere. Also remember that the center of curvature is located at 2 times the focal length. Okay, so here what we're going to do is we're going to actually solve a problem for a concave mirror. The focal length is 45 millimeters, the object is placed 25 millimeters away, and the height of the object is 15 millimeters. First thing I want you to notice is that I've already drawn my principal axis, and I've also drawn my mirror. Notice, though, that I draw it as a vertical straight line and not a curved line. The reason I do this is I'm not really sure what the curvature of that mirror is. I just know that it has a focal length of 45 millimeters. We assume when we're drawing ray diagrams that the curvature of the mirror is very, very small. In other words, we treat these as thin optics. So the first thing we're going to do is we're going to mark off our focal point, our center of curvature, and if you look at the ruler here, you can see that it's 10, 20, 30, 40, 45 millimeters away, and that the center of curvature is another 45 millimeters away from the focal point. Okay, so the focal point's located at 45 millimeters, and the center of curvature is at 90 millimeters. Okay, so the next thing we're going to do is we're going to draw our object. We know that our object is located 25 millimeters away, so we take our ruler and we measure out the 25 millimeters. So here you can see it's 25 millimeters away, and the height of our object is 15 millimeters high. So now that we've drawn our object, what we're going to now do is draw our rays. The first ray is drawn parallel to the principal axis. This is the principal axis. We draw our first ray parallel to that. Next, it goes through the focal point. So what you're going to do is you're going to take your ruler and you're going to make sure that it goes through the focal point. So you can draw a line through the focal point like that. Okay? Make sure that you draw your arrow going in and coming out of the mirror. I always like to circle the arrows so I know where they are. If I circle the outgoing ray arrow, then at least I know what 3 rays are actually making the image. This becomes very helpful when we get into more complicated ray diagrams. Okay, next ray is going to be through the focal point out parallel. So notice here, we're going to take our ruler, we're going to line it up with the focal point and the, oops, I just moved that, and our image, our object, and we're going to draw a line through the focal point and the top of the object as shown right here. Next, what we're going to do is have it come out parallel. So you take your ruler, line it up, and just draw a parallel line out, as you can see here. And here you can see the ray that goes in and the ray that comes out. Okay. The last ray that I'm going to draw goes through the center of curvature and comes right back out again. So there, you just put arrows on both ends. Now, let's look at the 3 rays that are coming out. So we have here, we have this one here, and we have this one here. Notice that none of these 3 rays appear to converge. Okay, so here's your 6 arrows. There's 1, there's 2, there's 3. We don't need to worry about the outgoing ones. And now what we're going to do is we're going to project these rays back in space since they don't converge. Okay, so we're going to take them back through the mirror as dashed lines. Here you can see the first line. The second one is this one, project it back. And the third one is this one, project it back. Then we draw our image where the lines or the rays intersect, which is right here. And there's our image. Next, what we need to do is we need to take our ruler and we need to physically measure the image distance. In this case, it looks like it's going to be approximately, let's see, 52 millimeters. Okay, so I get 52.5 millimeters from doing this before. Next, we're going to measure the height with our ruler. It ends up being 35.2 millimeters. Is it upright or inverted? That's right, it's upright. Is it real or virtual? It's going to be virtual because it's upright. Okay, is it magnified or demagnified? It's magnified. Okay, so there you go. That's how you get the properties of your image. Now, you can also do calculations here. So notice that when you do your calculation of your image distance, it ends up becoming negative. And that means that it's a virtual image. The magnification comes out positive. That tells me it's upright. Because the number is larger than 1, that tells me it's a larger image. Notice that also when you calculate the image height, it ends up being greater than the 15 that we started with. Okay, so virtual, upright, larger. That's the solution we get for this ray diagram. Okay, this is another ray diagram for a concave mirror. Notice in this case, the image is inverted. And that's because our object is beyond the center of curvature. Let me see if I also have one for a convex mirror. Here we go. So for a convex mirror, the light ray goes parallel to the principal axis. So this is your first ray right here. The second one is here. It goes parallel and through the focal point. Notice that for a convex mirror, that the focal point and the center of curvature are on the right-hand side. They're inside the mirror, okay? And that's because it's negative. The focal point here doesn't actually exist. It's actually projected into the mirror. Okay, so parallel through the focal point, this ray right here, out parallel, through the center of curvature is the green one, and out again along the same line. Look at these 3 rays that are outgoing. Notice they don't converge. We use our dash line, we take them back in space, and notice that they intersect here. Okay, you measure the distance from here to here with a ruler and the height. So you can see here that the height is going to be approximately 6 millimeters. And that if I measure the image distance, I end up getting about 18 millimeters. Okay, so 18 millimeters and a height about 5.9 millimeters. It's virtual, upright, and smaller. Okay, again, the key is if it's upright, same orientation as the object, that usually means it's a virtual image. Okay, I hope this has helped a little bit in drawing your ray diagrams. You're now set to be able to do those problems that are already in the optics E&M folder in Edmodo.